In this lesson, you're going to learn about the difference between empirical and molecular formulas. In an empirical formula, this formula shows the ratio of the different atoms that make up a compound. You can think of an empirical formula kind of like reducing a fraction or a ratio. It's going to be in the reduced form, so it's the smallest whole number ratio. A molecular formula, on the other hand, shows the actual number of atoms that make up each molecule. If you look, I have an example. If you have a compound that's made of, each molecule is made of 2 hydrogens and 2 oxygens, its molecular formula would be H2O2. I'm going to draw a picture of that here: an oxygen, another oxygen, and then a hydrogen, and another hydrogen. So its molecular formula would be H2O2 because each molecule has 2 hydrogen atoms and 2 oxygen atoms. That's the actual number of each. The empirical formula for that would be just HO. There's 1 oxygen for every hydrogen. So the empirical formula is kind of like a reduced version. We're going to look at a couple of examples of how to use this information. In the lab, you're not going to just go poof and get a formula for something. You've got to compare, and one way we can come up with a formula, besides volumes of gases that we've already looked at, is the mass of different elements that make up that compound. So we're going to look at a sample of rust. And we have done some lab work that shows that a sample of rust contains 69.94 grams of iron and 30.06 grams of oxygen. We ultimately want to compare the number of particles of iron and particles of oxygen, or atoms of iron and atoms of oxygen, so that we can figure out how many atoms of each there is and what's the ratio of iron atoms to oxygen atoms. So we're going to take both of those masses and convert them into moles. As we've already learned, the conversion factor between moles and mass is molar mass, so that is what we're going to employ here. Let's start with iron. The molar mass of iron is 55.845 grams of iron for every 1 mole. But we don't have 55.845 grams of iron. We actually have 69.94 grams. So it looks like a little more than a mole. And we want to figure out how many moles of iron that we have. So if you do some cross multiplication here, 69 times 1 equals 55.845x. And I'm going to divide both sides by 55.845, which means I'll be taking 69.94 divided by 55.845, and I got 1.25 moles of iron. I'm going to do the same thing with the mass of oxygen. Starting with oxygen's molar mass, there are 15.999 grams of oxygen in every 1 mole of oxygen. But we don't have 15.99 grams of oxygen. We actually have 30.06 grams of oxygen. So we want to know how many moles of oxygen we have. So again, cross multiply. 30 equals 15.999x. So 30 divided by 15.99 gives us the number of moles. And I got 1.88 moles of oxygen. Now neither of these are whole numbers, but we learned already that atoms tend to combine in simple whole number ratios. So along with keeping that in mind, we're going to look at what the simple whole number ratio of moles of iron to moles of oxygen would be. So if I compare 1.25 moles of iron, this is kind of something we did last chapter, to 1.88 moles of oxygen, what I end up getting is 0.66, which is 2 thirds, or that's saying there's 2 moles of iron in every 3 moles of oxygen. And remember, mole is just, each mole has the same number of particles, so that means for every 2 particles of iron, we have 3 particles of oxygen. So our formula is going to be Fe2O3. That's saying there's 2 iron for every 3 oxygen. We could write that as a for every statement, and we'll do that as well. So in this for every statement that I've just written, for every 2 moles of iron, there are 3 moles of oxygen, and that is exactly what this formula is telling us.